All right, we're going to now contrast the barotropic fluid to a baroclinic fluid and go back to our expression for d gamma dt to see what kind of circulation we get when we're dealing with a baroclinic fluid where density is a function of not only pressure but also temperature, and our lines of constant density need not be or not parallel necessarily to our lines of constant pressure. So d gamma dt is, again, as we talked about earlier, our area integral of 1 over rho squared of del rho cross del p dotted with n dA. And let's talk about, again, a baroclinic fluid. We're dealing with a situation where our density is a function of both pressure and temperature over here, such that we could have variations in, or our lines of constant density are not going to be parallel to our lines of constant pressure. What that comes down to is temperature gradients. We're going to potentially have horizontal temperature gradients take place, and that could be related to sea breeze boundaries or fronts. Outflow boundaries, for instance, where there's actually a skew between our lines of constant density and our lines of constant pressure, which we'll illustrate, for instance, over the a cross section between to the west here. Let's say we're dealing with a heat source being the Florida Peninsula out to the west, and then to the east we have the relatively colder Atlantic waters, or the air over the Atlantic waters is relatively colder over here. And so as a result, in the baroclinic atmosphere here, where we have the presence of a temperature gradient, we're going to be considering our lines of constant pressure and lines of constant density, which in this case are not going to be entirely parallel to each other as we go up with height in the atmosphere. When we consider, and let me move this down just a bit, because we have we have to consider the relationship between density and pressure and how they're going to be related to each other. Let's be very careful how we draw our lines of constant pressure over here. I'm going to show some slight tilt over here. Use P3 to indicate the highest pressure, lowest in the atmosphere. We know that we're going to be having these isobars slope up and over our colder Atlantic waters over here. Remember, as we're dealing with colder air over here, the density is going to be higher as all of our molecules of air are bunched together. They're not as dispersive, and so our pressure is going to be higher as well. But the slope here in these isobars is going to be much more modest than the slope of our lines of constant density. That's because pressure over here is considering not only the local temperature changes over here and the effect on density, but the entire mass of the column above it. We're considering the gravitational pull downward of all of the air molecules on that column of air, and we have to incorporate the entire vertical depth to get pressure over here. And so we're going to have much less slope of our lines of constant pressure than our lines of constant density. In other words, the lines of constant density are going to be much more sensitive to the differential heating than our lines of constant pressure over here, which will both be sloping up and over the colder air. So here's a line of constant pressure over here. Here is going up in the atmosphere, lower pressure, and even lower pressure, P2 than P1. Now, as I indicated earlier, and you can imagine some P4 over here with higher pressure closer to the over the Atlantic waters than over a P3 over here if we were to consider a horizontal cross-section over the warmer peninsula. And you can also draw in the lines of constant density. Again, with cold Atlantic waters, the density is going to be higher over here. So we'll draw rho 3. And it's going to be sloped much more so than our lines of constant pressure, owing to the fact that this will be much more sensitive, density will be much more sensitive to our changes in temperature. Here's rho 3, we'll draw rho 2 over here, and then we go towards the lowest values of density over our heat source over here. And so here's our distribution of pressure and density, and you can see here for our baroclinic fluid where we have the temperature gradient over here related to the baroclinic fluid, the fact we have baroclinicity over here associated with our temperature difference. we get skewness between our lines of constant density and our lines of constant pressure. And so now we know that this particular term over here, unlike for the barotropic fluid, for the baroclinic fluid, this is no longer going to be going to zero. Density is going to be a function of both pressure and temperature, with temperature variations occurring along our horizontal surfaces over here, as you can see. And this effectively, we have formed over here skewness between our lines of density and lines of constant density and lines of constant pressure. Now let's consider a closed path here, closed path C, somewhere in our baroclinic fluid. And I'm going to draw that in blue over here, just like this. And so we're just taking an arbitrary closed loop here in our baroclinic fluid, as you can see over here, and we're going to define clockwise orientation over here. So our DL vectors are all going clockwise around our closed loop over here. Now, if we were to draw where our dP is, rather our del P is going to be pointed, again, towards higher values of P, which are going to be orthogonal or perpendicular to our lines of constant pressure, and kind of like this. That's going to be del P. Towards higher values of pressure, and then perpendicular to our lines of constant pressure. Del rho, on the other hand, is going to be pointed towards our higher values of density, and perpendicular to our lines of constant density, like this over here. So let me indicate this over here more clearly. So now our del rho and del P are not parallel to each other in our baroclinic fluid. And as a result, when we take del rho cross del P, we have to use the right-hand rule to determine the resultant cross product direction. So if we point our finger, our index finger down del rho, and then our middle finger towards del P, just like that, our, in this case, thumb is going into the page over here, just like this. So del rho cross del P is going to be directed into the page. And I'll put that over here for our case, into the page. Another way we could approach this cross product is by initially putting our hand in the direction of del rho, the first part of the cross product, and then curling it in the direction of the, or toward our other component of our cross product, del P, which will go like this, and our thumb will go into the page or into the board just like this. And then n hat, this is just talking about the orientation of the closed loop and the resultant normal vector over here, which we're using the right-hand rule to determine based on the orientation of the closed loop, the DLs going around it, which is also going to be into the page based on these the blue orientation or blue marked orientation around our closed loop here, also into the page. So we have a vector that's going into the board, dotted with a vector that's going into the board, and the result over here is a positive value, or positive circulation is imparted to this closed loop. But what does that positive circulation actually mean? Well, remember, gamma is just equal to the closed path integral of u dotted with dl. So if we're having an increase in gamma, or positive values of d gamma dt, an increase in gamma, and we know that the closed path or the gamma can be expressed as the closed path integral of the tangential velocity, then our tangential velocity over here is going, based on u dot dl, is going to have to be positive gains over here. So these positive gains mean that our u dotted with dl is going to have to be positive as well. So if u dot dl is positive, our flow needs to be oriented with a component parallel to our dl vectors marked by the blue orientation over here, which means for u dot dl or u dot dl to be positive, u has to be parallel to this part of our closed loop orientation, and u is going to have a component along or parallel to our closed loop just like this, generating a circulation, in this case clockwise, matching the orientation of our closed loop. And so as a result, we get a circulation induced such that we have rising motion above our heat source over land, sinking motion over or subsidence over our colder region over here, and then a component of the circulation from higher density, higher pressure, so higher density towards lower density here to complete the circulation, and then opposite that, higher in the atmosphere to complete the circulation. So the result is the generation of a circulation with ascent over the heat source and subsidence over the colder source. So our differential heating drives the circulation with ascent over the lower density, hotter air, and then subsidence over the colder air, higher density part of our background thermal gradient. Now, if we were to choose, we arbitrarily chose around our closed loop to go with a clockwise loop. We could have chosen in this particular case to have gone with a, let's do this over here in green over here. Let's say that we chose our closed loop to go counterclockwise, which I'll show like this. So counterclockwise alternatively. Well, as a result, our n-hat vector would be pointing in this case out of the page or out of the board like this. But del rho cross del p, that's completely independent of how we define our coordinate system or the orientation of the loop. So that's still going to be going, in this case, into the page. So into the page, dotted with out of the page, anti-parallel. So we're going to be dealing with, in this case, a dot product that goes to negative values. So given a counterclockwise orientation around our loop, and in this case, a loss of, or d gamma dt being negative, or a loss of circulation, what that means is that u would have to be anti-parallel to dl. Well, if dl is going counterclockwise, then u would have to go clockwise, such that they're anti-parallel, and as a result, we get the exact same circulation as we found before. Ascent over the heat source, substance over the cold source, such that we end up getting our u over here be opposite in direction to our dl vectors that were, in this case, now arbitrarily chosen to go, in this case, in a counterclockwise direction. And we still get the same physical response, being this vertical circulation featuring ascent over the heat source and subsidence over the colder air source over here. And so as a result, we see that indeed this vertical circulation is consistent no matter how we choose the orientation of our closed loop.